first couple of questions on the document for this class can easily be answered in terms of the definition of the radian and the definition of pi, as opposed to using formulas that we might confuse and that I see being confused. Okay, so the definition of a radian is that the arc distance is equal to the radius. Okay, and we've discussed that. That's a short definition, but it's characterized by the fact that the arc distance on a circle for an angle of 1 radian is equal to the radius of the circle. So definition of pi is simply the ratio of circumference to diameter of a circle. You don't need formulas, you just need those two definitions. The formulas come immediately from the definitions, but I'm going to go back to the definitions at every opportunity. Okay, so omega, angular velocity of 2 revolutions per second, is equal to how many radians per second? Well, a revolution is once all the way around the circle. The distance around the circle is pi times the diameter, or 2 pi times the radius. Each radian corresponds to an arc distance equal to the radius. So if you go all the way around the circle, you're going around 2 pi times the radius. You have 2 pi radians. Okay, your arc distance around the circle is 2 pi times the radius. The arc distance for 1 radian is equal to the radius, so around the circle is 2 pi radians. Digest that statement, write it down, make sure you understand it. It helps you visualize radians, helps you understand what's going on here. Alternatively, and what we're trying to find out is how fast an object moving around a circle of radius 40 centimeters is actually moving if the system is rotating about an axis at 2 revolutions per second. Okay, the distance for 1 revolution is then the circumference of a circle of 40 centimeter radius. That's going to be pi times the diameter of the circle, or 2 pi times the radius, 80 pi centimeters for every revolution. What's the speed? Okay, the speed of something moving around this circle with this angular velocity is going to be the 80 pi centimeters per revolution, distance traveled per revolution, multiplied by 2 revolutions per second, which gives you 160 pi centimeters per second. We don't need a bunch of formulas, we simply need to understand circles and radians and pi. Alternatively, you could say the speed is what? 4 pi radians per second. Each radian corresponds to the distance equal to the radius, so you got 40 centimeters for every radian. Now, it has to be visualized, has to be understood a little more deeply than just a superficial plug into a formula, but once it is understood, again, you have a depth of understanding that you don't get by manipulating formulas and getting things in the easiest short-term with the easiest short-term strategy. Okay, a long-term strategy is to understand this, and it's not hard to understand. In any case, you multiply that out, you get 160 pi centimeters per second. So reasoning from the definition of radian, definition of pi, and a little bit of common sense, we obtain these results without using any meaningless formulas. Now, in terms of these results, it's good to go look at the formulas and see what they're telling you and see how you understand the formula in terms of these common sense calculations. There's nothing wrong with formulas if you use them to reinforce something you understand, or if you use them as a basis for understanding something at this level. Okay, well, now here I've just repeated how these statements follow from these definitions, and you see how they've been used in reasoning out the result. Now we're ultimately asked, what's the kinetic energy of a mass of 100 grams moving in this manner? So you have a 100-gram mass mounted on a beam or something that constrains it to move in a 40 centimeter circle, a circle of radius 40 centimeters. And at a certain instant, it's moving at 2 revolutions per second. So how fast is it going? We can use that to calculate the kinetic energy, 1/2 mv squared. Well, we got how fast it's going here or here. We've got the mass, 100 grams. So we plug this in, and we get a result in ergs. 1.2 times 2 to the 7th ergs, actually probably closer to 1.3. No, probably closer to 1.2. And that turns out to be 1.2 joules, if we understand what an erg is and how it's related to joules. Just how do the units of grams and centimeters relate to the units of kilograms and meters? And how does that relate to the conversion of energy? Okay. Yeah, that's all we want to say about this right now.